Okay, in this problem, we see that there's a spring attached to there's actually a train with a spring attached to it, and that's attached to a 2 kilogram block. And the toy train is going to pull on the block and try to move it forward. So there's a coefficient of static friction that's holding the block in place, and the spring is at its equilibrium when t equals 0. So it's not stretched, it's not compressed. And the spring starts to move, and the block doesn't move right away. And so what we want to know is how long, after what amount of time, does the block slip? So what we want to do first is we'll start with a free body diagram. So let's look at our block, and we'll draw our boundary. And so we see that we have the force of the normal, we have the force of gravity, we have the force of static friction against the motion, and then we have the force of the spring. So if we draw our free body diagram, right, our normal force is balancing our force of gravity, so these two are equal. And our force of the spring is equal to our force of static friction until right before the block starts to move. So what that means is that our sum of the forces in the y direction are equal to 0, and the sum of the forces in our x direction are equal to 0. So they're balanced. So if we just think about some of the forces in our y direction, that'll give us the information we need for the force of static friction. So we've got force of the normal minus Fg is equal to 0. So force of the normal is equal to Fg. I just brought Fg to the other side of the equal sign. And we know that Fg is equal to mg. So we've got force of the normal is equal to mg. Well, what about some of the forces in the x direction? We've got force of the spring minus the force of friction is equal to 0. So that then we can just bring the force of friction to the other side of I can add to both sides and bring the force of friction to the right of my equal sign, equals the force of friction. And we know then the force of the spring then is equal to mu static friction times the force of the normal. I can plug in now for my spring, and I'm going to have k delta x is equal to mu, and my force of the normal is mg. So I can solve for delta x. So if I divide both sides by k, divide by k, I'm going to have delta x is equal to mu mg over k, and this is static friction, k. So if I want to plug in, then I'm going to have delta x is equal to mu. So the number I'm putting in for mu is 0.6. And so this is the largest the static friction can be before it starts to move. So I'll put a little s there. So this is going to be 0.6 times the block is 2 kilograms. Gravity is 9.8 meters per second squared, and K is 50 newtons per meter. And when I plug that in, I'm going to get delta x is equal to 0.235 meters, or delta x is equal to 23.5 centimeters. Okay, so now how do I find the time? Well, I can use one of my kinematic equations. So x final is equal to x initial plus VIX delta t. And I know that x final minus x initial is equal to VIX delta t. All I did was I just subtracted xi from both sides here, right? So, and so x final minus x initial is my delta x is equal to VIX delta t. And I'm solving for delta t. So delta t is equal to delta x over VIX. Plugging in, I get 23.5 centimeters. And my initial velocity, the problem tells me the initial velocity is right here, 5 centimeters per second. So I'm going to plug in 5 centimeters. 5. 5 centimeters per second. And so I find then that delta T is equal to 4.7 seconds. So that's the time it takes for the little toy train to pull against the block. And then after 4.7 seconds, the block, the spring has exerted enough force to be able to overcome the static friction and get the block moving.